Hi. So in today's lecture, we are going to continue our discussion of uh, a peek into the techniques used in proving hardness of approximation. So last time, if you recall, what we had seen was this notion of gap problems, that is defining versions of the optimization problems where there's a gap between the yes and no instances. So in some way, it was a yes-no decision version of the approximation or optimization version of the problem. Okay. And we saw how it relates to proving hardness of approximation results. Next, we had looked at reductions between problems, which, if we recall, was how we showed NP completeness in the first place for many of these problems, except that now they came with the extra property that the reductions we use either introduced a gap, that is starting from a 3-sat instance, they gave a gap between the yes and no instances and hence gave us a gap problem, or when going from a gap problem to another gap problem, they preserve the gap in some meaningful way. Okay, so hardness of approximation for your first problem also implied a hardness of approximation for your second problem. And then we had stated the Pcp theorem in one of its forms, which is the hardness of the max 3-sat problem, okay, between the differentiating between satisfying completely satisfiable instances to instances where at most you can satisfy some 1 minus epsilon naught fraction of the clauses. Okay, and using that gapped version, we had shown a gap preserving reduction that showed hardness of approximation for min vertex cover and max cliques up to some constant factor. So today what we are going to do is first introduce the idea of gap amplification. Okay, and what we'll do here is we'll take the result for max clique that we had shown last time, hardness of approximating until some constant factor which was dependent upon the gap of the original max 3-sat problem that we started with. And we'll show how to amplify this gap between the yes and no instances, okay, to get better hardness of approximation results for the max clique problem itself. Okay. Next, we are going to go on to the probabilistically checkable proofs view of NP. Okay. And this had given you a slight introduction to last time when it mentioned about a verifier checking the proofs. So we are going to go back to that in a little more detail and give you a second form of the Pcp theorem. Okay. And using the second form, we are going to see hardness of approximation for max exact 3-sat, okay, which is 3-sat with every clause containing exactly 3 literals. Okay. And finally, we'll come down to the problems of label cover and unique games. These are the label cover problem is kind of the mother of hardness results in some sense, just like 3-sat was for showing NP hardness or NP completeness. Okay, so to show that a problem is NP hard, invariably you can reduce from some version of this label cover problem to start with. Okay. And we'll state the Pcp theorem in its third form, which will involve the label cover problem. And if time permits, I will show omega log n, or at least give an idea of the omega log n hardness for set cover. Okay. So with that, let's go on to today's lecture. So the first topic, as I said, is going to be gap amplification. Now, if you recall what we had shown last time, we had shown the following gap version of the clique problem was hard. So you had a graph on 3m vertices, okay, where m was the number of clauses in your formula to begin with, in your 3-sat formula from which you reduce from, right? So that doesn't really matter over here. We had a graph on 3m vertices, and you had to decide whether there's a independent set, or rather, let me say, a clique in the complement graph of size at least 3m or less than equal to 1 minus epsilon naught m. Okay, and this problem we had shown was NP hard because the gap 3-sat problem was NP hard, and this was for some particular epsilon naught, where epsilon naught was some really small number like 0.0001 or something. Okay. Now, what was the issue with such a hardness result? Well, the problem is basically the fact that the gap over here, that is 3m. Oh, this should be m actually. The gap between the yes and no instances is really tiny. So you have m and then you have something like 1 minus epsilon naught m, which is like 0.9999 m. Okay. Now this gap is really tiny. So one could think of this as saying that, well, this is really close to m versus m minus 1. Not exactly, because for m really large, this is a significant constant factor gap. But the question that one should be asking possibly is, well, I can't really find cliques in a graph to any good approximation factor. In that case, is it actually true that clique is hard to m versus something like 0.0001 m? So is this problem hard, where the yes instances are here and the no instances are here? Okay. And it turns out that the answer to this is indeed yes. And all we'll do is actually give a gap amplifying procedure which amplifies kind of literally the gap between m and 0.99 m to between m and 0.001 m for some other m. Okay, so maybe I'll call this m prime for a graph on similar number of vertices. Okay, so how do we show this? Well, the procedure is the following. I'm going to show that given this result, I'm going to construct another graph G, okay, where we are going to have that the gap between the yes and no instances is some 1 minus epsilon naught squared. I'm going to call this G cross G, which is a product operation on the graph. Okay, what does G cross G mean? Well, this is a new graph with vertex set V cross V and edge set being some E prime, where I'm going to define E prime now. Now the vertex set over here is basically every vertex is a pair of vertices in the old graph. Okay. And every edge here, notice that in this new graph, the vertices are pairs of vertices. So the edge between u1 v1 and u2 v2 if and only if, basically what I want is that there are edges between both u1 and u2 and v1 and v2, or they are equal. So this edge, if and only if u1 is equal to u2 or u1 u2 element of the edge set of the graph, and v1 is equal to v2 or v1 v2 is in the edge set of the graph. Okay, so now if your original graph had got some n vertices, then G cross G has n squared vertices, okay, with edges defined accordingly. So for instance, if 1, 2 and 3, 4 were edges in your original graph, then G cross G has got edges between so now this become vertices. In fact, let me simplify this example over here. Instead of having 4 vertices, I'm going to take G to be just a 3 vertex graph with 1, 2, 3 as the vertices. Okay, then G cross G has got 9 vertices, each corresponding to 1, 1, 1, 2, so on, all the way until 3, 3. So all of these 9 vertices are there, and for instance, there will be an edge between 1, 2 and 2, 3. Okay, and so on and so forth. So there will be an edge between 2, 3 and 1, 2 also, and so on and so forth. Okay. So now we are going to relate the size of cliques in G and G cross G. Okay, so the claim is the following. So if the size of clique in G cross G is equal to the size of clique in G squared, where omega is max clique. The proof is actually quite simple. I'm going to show only one side of this part, that is, I'll show that the size of max clique in G cross G is greater than equal to the size of max clique in G squared. The other side is equally easy to show, and I'll leave it as an exercise. Okay. Now, if S is a clique in G, then I claim that S cross S is a clique in G cross G. Okay, and this is simple to verify, because if you had because all you need to verify is that for any pair of vertices uv and u prime v prime, if they are in S cross S, then you will notice that because u and u prime are in S, there is indeed an edge between this, and there is an edge in the original graph between v and v prime, u prime E of G implies there's an edge between these two vertices in G cross G. Okay, and hence S cross S is a clique. And of course, the size of S cross S is the squared of S. So there is a clique of size at least omega of G squared in G times G. Yeah. Now the other way, which is an exercise, is all you have to show is that if you take a clique in G cross G, then there is a clique of size square root of that in G. And you show this just by showing this fact by just taking either the left coordinates of the vertices or the right coordinates of the vertices. Okay, that's quite easy for you to convince yourself. Now, how will we use this? What have we gotten over here? Well, if you apply this to our original gap problem where you had a G with n vertices and you're asking is there a clique of size n over 3? Notice that I've switched notation from having 3m vertices in the graph G to having n vertices in the graph G to something like this, and this was distinguishing between the yes and no instances. Here was NP hard. Notice that from this we have got a graph G cross G on n squared vertices, and we have found a reduction which maps the yes instances to the yes instances of here, except that now this is greater than n squared divided by 9, and this here is less than equal to implies the gap factor between the yes and no instances in this new G cross G graph is like 1 minus epsilon 0 squared. Okay, whereas the gap between the yes and no instances was just 1 minus epsilon 0. Now, what has this done? Effectively, you can see that this has improved the gap between what was, say, 1 versus 1 minus epsilon 0 multiplied by some same factor to 1 versus 1 minus epsilon 0 whole squared. Okay, and this has come at a cost, that is, you're increasing the size of the graph G, but you're still increasing it to just the square of the number of vertices. Okay, so if you could solve the G cross G problem, you could solve the G problem. But then why stop at just a two-way graph product? You could take the graph product some k times and still end up. So you started off with this. And what you would end up is with a graph which I'll call G raised to k. Okay, where the S instances are greater than equal to n over 3 raised to k, and the no instances are 1 minus epsilon naught raised to k n over 3 raised to k, which means the yes to no instance gap is 1 minus epsilon 0 whole raised to k. Okay, so this is the factor gap between the yes and no instances. And what has this given us? This says that if the reduction over here, the k time reduction, is polynomial time, okay, then we actually have a map that amplifies the gap between the yes and no instances within the same problem domain. Both are max clique problems, both in G and G raised to k. So this gives us, so when is this reduction polynomial time? Well, every single step of the reduction is polynomial time. So you can at most hope k to be polynomial, to be constant. So it can be any constant as large as you want in order to keep the whole reduction polynomial time. So for any constant k, the reduction G to G raised to k is polytime. Okay, you get a graph of size n raised to k vertices. And this gives us that gap between 1 comma 1 minus epsilon 0 raised to k of max clique, where again I'm implicitly ignoring the multiplicative factors here, which is something like n over 3 raised to k. It doesn't really matter for our approximation, so maybe I'll just put it as some alpha is NP hard. Okay, implies, but notice that I can take to be k to be any constant, therefore 1 minus epsilon naught raised to k can be any small enough constant, which means that approximating max clique to any constant factor is NP hard. Okay. Now what would have happened if we had done this reduction to a non-polynomial number of times? Say we had taken k to be some log n times. Let me forget the order over here. Then what would happen? Well, the G raised to k instance would have size n raised to log n, right? On the other hand, we would get 1 minus epsilon 0 raised to log n. Now what is 1 minus epsilon 0 raised to log n? Well, this is something like n raised to epsilon 0, which, if you notice, is a much stronger hardness factor than just the constant hardness factor that we have figured here. Okay, so it is n raised to epsilon 0. Approximation is also difficult. Rather, it should be n raised to minus epsilon 0. Okay, now the point about this is the following. We started out with a 3-sat instance of size some n. Okay, and if you had a polynomial time algorithm for max clique, what does it that approximates it to n raised to minus some epsilon 0? Okay, what does that mean? That means that you have, so here you have g raised to k for some large k. Let me call this graph g tilde. Okay, and you had a polytime algo for max clique. Then the yes instances here got mapped here, and the no instances got mapped to this, where the gap was n raised to minus epsilon 0, the ratio. Now the point, as I want to say, is that if polytime algo here, okay, in the number of vertices in the graph, would translate back to something like a poly of n raised to order log n algo for SAT. Okay, because the graph G was n raised to log n sized. Okay, because you had this initial gap introducing reduction from 3 SAT into a gap clique, and then you amplified that gap all this way. Okay. So what we can say from this, if you think about it for a bit, is that unless NP is in, or NP complete problems have deterministic algorithms that run in n raised to order log n, no 1 over n raised to epsilon 0 approx for max clique, and this is polytime. Okay, so this might be a little difficult to grasp at your first instance when you're seeing this, but the point is that we don't expect to have even quasi-polynomial or n raised to order log n time algorithms for NP complete problems. Okay, in fact, there are hypotheses that say that you can have only exponential time algorithms for these. So even this is highly unlikely, or believed to be highly unlikely. Okay. And hence this is also a valid assumption to start off with, which is slightly stronger than P not equal to NP. Okay. Another way to see this is that the F over here that creates a n raised to minus epsilon 0 gap between the no and the yes instances, it takes time, not polynomial time, but n raised to order log n time. So I won't stress this factor more at this point, but it's useful to remember that this again falls in the same line of hardness results, or in fact all hardness results that we prove that if phi had a polytime algo, then you had this something bad happens. Okay. And by something bad, it was either usually P not equal to NP, and in this part here, it was NP. You have n raised to log n time algorithms for NP. Okay, so that's what I wanted to say about gap amplification and clique. Now, small word about the Pcp theorem. If you notice what it is saying, as we had stated it last time, was that gap 1 comma 1 minus epsilon naught max CSAT is NP hard, right? Okay, which meant that we had a gap introducing reduction from just the 3-SAT problem, which was a decision yes no problem, is phi satisfiable or not, into this gap problem where you had all m clauses satisfiable, or a fraction 1 of the clauses were satisfiable, versus less than 1 minus epsilon naught was satisfiable. You can think of this also as some sort of gap amplifying reduction, because quite frankly what you're looking at in this 3-SAT yes no decision problem is the yes have got m clauses satisfiable versus m minus 1 satisfiable, is the yes no instance, and hence there is a non-zero ratio between the yes and no instances. Or rather, let me put the no by yes because it's a maximization problem. Which is 1 minus 1 over m, and what you want here rather is this 1 minus 1 over m, where this 1 over m is not a constant, so somehow be amplified to 1 minus some constant epsilon naught. Okay, and that is the whole thing by the PCP theorem. um, what the PCP theorem shows, it shows that you can actually amplify the gap in this way. So this more or less finishes the first unit of today, where we dealt with gap amplification, and now we'll move on to the proof checking version of the PCP theorem. So let's start here with the definition of NP as we have seen it. Okay, so for NP problems, what you have is a verifier V. Okay, now you have a problem pi. Let us say that is that P is CSAT or not. Okay, and so this verifier V has access to the formula phi. Okay, and also what CSAT being in NP means is that there is a proof pi such that if the given instance phi is a yes instance, that is, it is satisfiable, then the verifier can actually check a proof which is polycized and say yes correctly. Okay, so correct formulas come with a proof. In this case, if it's a 3-sat formula, for instance, then the proof is just the assignment of the vertices, the assignment of 0, 1 values to the variables involved in phi. Okay. And similarly, if phi was a no instance, implies whatever the proof that might come across, the verifier will have to say no. Okay. Now the key point to note in this is that the verifier first of all runs in polynomial time. And the verifier looks at the entire proof before deciding whether phi is satisfiable or not, or may choose to look at the entire proof. Now what we are going to look at is a probabilistic version of this. Okay. As stated, the verifier is deterministic, and we're going to look at probabilistic verifiers. That under the same setting, given phi, p element of yes implies, now what does the verifier do? Well, the verifier tosses coins. The verifier looks at the outcome of these coins and decides to probe certain locations in the proof. Okay. And then depending on the result of that probe, that is, the verifier does not look at the entire proof, but say checks some small number of locations in the proof. And just depending on this, the verifier can output a result. That is, the verifier's estimate that indeed the proof is correct and phi is satisfiable. So what would we expect from such a verifier? Well, we would want at least that if phi is a 3-sat instance, then there should be a proof pi such that the probability that the verifier says yes is large, okay, is greater than C. Think of C as being say 2/3 or something. And if phi is a no instance, so I want you to compare this to the NP proof above. Then for all proofs, the probability that we checks these random locations and says yes should be less than equal to S, and think of S as a small number, say 1/10 or something. It doesn't really matter what this number is as long as it's gap, as long as there's a gap between C and S. Okay. Now if you look at this, there are certain parameters that such verifiers are bounded by. The first one is the number of coins tossed at this point. The second one is the number of locations that the verifier queries. For instance, if the verifier could have queried all the locations in the proof, it would have gone back to the previous definition of NP. Okay. So the certain, let me say, queries Q locations in the proof. And of course, there is the completeness and soundness probabilities. Okay. So the parameters here are Q. Let me start with R, which is number of random coins. Q, which is number of queries to the proof, or how many probes are made based on the outcome of the random coins. What the random coins determine are the exact locations in the proof that are probed. The third thing is, of course, what function the verifier is using to check. So most verifiers that we'll be dealing with will use just a deterministic function to check, okay, based on the outcome. Finally, C, which is the probability of saying yes on actually yes instances. This is often called the completeness probability, or just completeness as a property. And S is often called the soundness, which is the probability with which it says yes to the wrong instances. Okay. Now clearly, if you go back to the previous definition of NP in the deterministic world, you will see that it corresponds to each of these parameters being something in particular. You'll find that NP is trivially the deterministic definition above that was just given over here is equivalent to R being some order log n, where n is the size of the instance, Q being again the size of the proof, in fact R is close to 0. Okay, Q is the size of the proof itself, C is equal to 1 and S equal to 0. Okay, so this is the deterministic version of this probabilistic verifier that we defined as NP. So clearly what we would like to do is, by introducing randomness, we want to make this small. Okay, keep the function that we used to simple, but I will not mention that in too much detail at this point. The completeness we want to make large and as close to 1 as possible. And the soundness we want to get it down to 0. And this is what we want. So in this case, if you manage to make Q small, manage to use few random coins, make C large and S small, you're in some sense intuitively getting to more and more efficient verifiers, okay, who can query small number of locations in the proof and decide with high probability whether the instance given is a yes or a no instance. Now you can think of this PCP or probabilistic PCP as accepting or rejecting strings that are given. For instance, the strings may correspond to instances of 3SAT or a graph G that you want to check is 3 colorable or not, so on and so forth. So in fact, what it is doing is it defines a language class. Okay, and what we have said above with these parameters is the language class that is recognized by probabilistically checkable verifiers, which we'll call as PCP, with subscript C, S of R, Q. Okay. So all of these R, Q, and possibly C and S are all functions of N. Okay, so another way of saying that NP is the definition of NP is just stating that NP is a subset, that is, the class of languages in NP are precisely those that can be recognized by such probabilistic verifiers with completeness 1, soundness 0, randomness 0, and number of queries being a polynomial. Okay, that is, it checks the entire polynomial size proof. Now at this point, I have not told you anything about what function the verifier is using to decide yes or no. All that we want as of now is that it runs in polynomial time, but we'll see that this can be quite important in proving hardness of approximation results. Okay. Now, this form of one-shot verification of a given proof is not the only type of proof system that exists. In fact, other classes of proof systems have been explored a lot in complexity. In particular, if you have interaction between the prover and the verifier, then it is called Arthur Merlin one round. Then you have interactive proofs where there can be back and forth rounds between the prover and verifier, and then the prover finally is convinced that the statement is true or is convinced that the statement is false with good probabilities. Okay. Then you have multi-prover interactive proofs where you also have not just one prover, but you can have k provers all submitting proofs to the verifier and the verifier using it to judge the correctness. You have zero knowledge proofs, etc., so on and so forth. So these are all well studied objects in complexity theory, and this one shot PCP that is here is just one of these many classes of proof systems that are studied. Now it turns out that this class, the PCP class or the PCP theorem, was indeed developed as a way to understand where does NP fit into this whole hierarchy, okay, of this. For instance, MIP is known to be equal to NEXP, and in fact it was proven in a very recent result that if you allow the provers, if they verifier to share quantumness or entangled bits, then MIP star is actually the class of all recursively enumerable languages. Okay, so this is a very recent result, but anyway, maybe I'm going too much into complexity theory at this point. Let me come back to the question at hand. Okay, we wanted to look at more and more efficient verifiers, probabilistic verifiers for the class NP, and another form of the PCP theorem is exactly that. The PCP theorem says that NP is a subset of PCP 1, half, order log n, and 3. So in fact, sorry, this should be a constant C, okay, and this is actually a remarkable result because it says that all you need to do is query some constant number of bits of the proof and you can verify with good probability whether an instance is satisfiable or not. So this was the original form of the PCP theorem, and we'll see with a little work that, in fact, we may not see it here. This form 2 is actually in some sense equivalent to form 1. But using one of the reductions that we'll see soon, you will get an idea of why this is true. Now, where do we go from here? Well, I'm going to state a slightly different version of the PCP theorem, which I'm going to call form 2.5, which is going to kind of restrict the functions that the verifier can use, and it is going to bring down the number of queries to 3. Now, a notable aspect of this, of course, this constant query size and how low we can get it. And in that vein, the following is due to Hastad. That you need to query. So note, remember that this is the query size into the proof. So you're given a proof, you just want to check 3 bits of the proof and then conclude. Okay. Further, the verifier only uses the parity of the bits that it queries. Okay. And this is really cool because you've got it down to really 3 queries, but notice that we have lost out a little on the completeness on soundness. We no longer have a differentiation between 1 minus 1 and something, and we'll see in a moment why that is needed, why the 1 minus epsilon is needed, but it is a difference between 1 minus epsilon and half plus delta. And I should quantify these constants, that there exists epsilon comma delta, which are constants such that this holds. Oh, I stand corrected. This holds for all epsilon comma delta greater than 0 such that epsilon delta are constants. Similarly, in the upper part, it is there exists a constant c greater than 0 such that the above holds. So what does this mean? That suppose I want to verify that a given formula, for instance, is actually satisfiable, then the proof can be presented in such a form. Notice now that there is no restriction on what proof is presented actually to the verifier. It need not be of the exact form that you just give the assignments to the variables, the 0 1 assignments to the variables. Rather, it could be some garbled up form that is useful to the verifier. Okay, so the verifier might request that you give the proof in a certain form, and then you have to produce the proof in that form, and then the verifier can check it. Okay. So the verifier, what all it does is given the proof in this encoded form. Okay. The verifier chooses 3 locations based on the outcome of the random coin tosses. Let me say it is xi1, xi2, xi3, and looks at xi1 XOR xi2 XOR xi3 and decides is this 1 or 0, and appropriately says yes or no. Okay, so the decision again depends upon the verifier. It may say yes on 1 or yes on 0 depending on what random coins come up. Now, another point that I did not really emphasize in the previous part is the role of the randomness and how a bound on it actually determines the length of the proof. So if the randomness is something like log n, then you can query at most 2 raised to log n locations in the proof. There are 2 raised to log n possible outcomes of the random coin tosses that are possible, which is a polynomial in n. Okay, and which means that the number of locations in the proof can be at most polynomial. which is why the bound on R being polynomial is kind of important. Now, this view of NP as being a checkable proof system might seem a little alienated from what you have seen till now, which is the hardness of approximating problems in terms of gap. In terms of gap formulations, okay. And what I want to show next is that actually this whole idea of a verifier checking a proof randomly and saying something with some probability is nothing but a constraint satisfaction problem hidden in some way. Okay, so this verifier, as I've shown here, has access to the fee, okay, where I'm always taking an input formula to the verifier that it has to decide yes or no for. Now, let us consider the following problem, which is formulated based on what the verifier is going to do. Okay. So the verifier here, let us say that the verifier is a valid verifier for the 3-sat problem, which is a NP complete problem. Okay. So the verifier tosses some R random coins where R is order log n. Okay, comes up with locations to query in the proofs and checks the parity of them to be some equal to some B. Now, so let us regard the locations in the proof as variables. Okay, so every bit in the proof pi is made up of bits. So you can think of these as variables which you need to substitute to find a valid proof, right? And what is the verifier going to check? Well, on random coin outcome R, maybe it checks the bits whether x1 or x7 or x10 is equal to 1, say. Okay, for random coin outcome 2, it checks whether x15 or x27 or x100 is equal to 0. Okay, so these are the checks that are to be performed by the verifier depending on the outcome of the random coin tosses. Now, if you keep enumerating the what are the checks that the verifier does in terms of the locations regarded as variables, what do you have? Well, I claim that you come back to a constraint satisfaction problem. Okay, so if you list out at outcome R, you have something like the first bit XOR the second bit XOR, well, these indices depend upon R, so I should write these as R, and it checks whether the XOR of this is equal to some B of R, right? How many such equations are there? So you have 2 raised to R equations where R is equal to the total number of random coins, which we know is order log n, right? So this is a system of equations in some variables, right? And what are you asking? You're saying that if my input here, which is phi, is a yes instance, because there exists a verifier, I know that there is a proof. So there is a set of assignments to these variables. That satisfies greater than equal to 1 minus epsilon fraction of the equations, right? And if you have phi in no, implies for any assignment we have at most half plus delta fraction of these equations are going to be satisfied, because the verifier accepts at most with probability half plus delta for all assignments. And now what this tells you immediately is you have reformulated via this verifier concept your probabilistically checkable verifier as whether a set of equations has got a solution that satisfies either a 1 minus epsilon fraction, or whatever you try to the assignments to the variable satisfy at most a half plus delta fraction. So this is indeed a gap problem, right? So it is a gap problem on the problem of set of linear or gap problem for satisfying a number of linear equations. I'll call this uh, problem the Max Thielen problem, in which you're given a set of equations in three variables of the form x1 or xi or xj or xk is equal to b, right? So these are the equations, and you might have m equations where the xi's are 0, 1 and b's are fixed constants that are given to you. How many of these can you satisfy? And what we have shown before, what we have shown just now using this reduction, is that the problem of deciding between 1 minus epsilon or half plus delta of Max Thielen is NP hard. Because what we have done is, via the existence of this verifier in terms of the Pcp theorem, we have actually produced a reduction all the way from an NP complete problem, for instance 3-SAT, to this gap Max Thielen problem. Okay. So this Max Thielen problem is kind of a relative, is the discrete analog of whether a set of linear systems is soluble or not, right? And we know that at least in the real world, given a set of equations, you can immediately determine whether there is a feasible solution or not. Of course, the XORs will be replaced by pluses. That is by either Gaussian elimination, of course, or you have seen linear programming. We have been solving these linear systems or saying that they are solvable. So Gaussian elimination works over the finite field as well. What I mean by finite field, or F2, these are just equations over numbers 0, 1. Okay. So if you're familiar with finite fields, you will understand this. These are just linear equations over F2. And because these are linear equations over S2 over F2, you can understand why this gap is important, because you can apply an analog of Gaussian elimination in this finite field in order to check whether it's perfectly satisfiable or not. Is there an assignment that satisfies all of the equations at once? So there might be some m equations, so on and so forth. So here we have shown that Pcp theorem of the form 2.5 stated above in the prover verifier world is exactly equal to this. In fact, if you go back to the Max Clique problem that we showed hardness of using a standard reduction, gadget based reduction from the gap 3-SAT instance, you can actually view almost any constraint satisfaction problem expressed uh, as a PCP verifier in terms of actually an underlying max clique problem. Okay, and it was in this context of that is the approximation of max clique via PCP verifiers that the connection of hardness of approximation to proof checking was discovered. Okay. So if that comment wasn't very clear to you, maybe I'll include it as part of a small exercise. Uh, Now, to come back to what we have here in terms of max Thielen, what we have shown finally is the following, that if you take any NP complete problem, let me say for representative CSAT with yes, no, the PCP theorem states that there is a map from the yes instances via both use F. There's a map to a gap 1 minus epsilon versus half plus delta of max Thielen. Okay, and F is of course polytime. Now what I want to show using this is that it is NP hard to approximate max CSAT. And this holds for any epsilon greater than equal to 0, greater than 0, which is a constant, okay, epsilon prime. Now what we are going to do for this is going to use the max Thielen gap that I've seen above, which is nothing but PCP theorem 2.5 restated. And the crucial fact over here is the predicate that is used, that is max Thielen, which is the XOR of 3 bits. So you start with a max Thielen instance, and let us say it has n variables, m clauses. Okay, and what we are going to do is a direct reduction to TreeSat, max CSAT actually. So we have, suppose you have an equation, so here's my Thielen instance, and you have a clause or an equation in that of the form xi1 XOR xi2 XOR xi3 is equal to 1. So you transform that into a set of clauses over here which state that, so for every equation in the Thielen instance, I'll get 3 clauses which you can guess to be equal to, well, actually 4 clauses, and so on. So these are the 4 clauses that I will write down if the XOR of these is equal to 1, and it's not very difficult to guess what it will be analogously if the XOR of some 3 bits is equal to 0 is one of your Thielen equations. Okay, so the CSAT if, yes, I'll leave writing out the explicit equations out to you. Now it's easy to verify the following. First of all, some simple observations. The Thielen instance, if it has m equations, CSAT has got 4m clauses, right? And suppose an equation is satisfied, then all of the 4 clauses corresponding to it in the CSAT instance are satisfied. Okay, and suppose the equation by some fixed assignment to the n variables in the 3-line world is not satisfied. This implies that at most 3 clauses are satisfied. Okay, by 3 I mean 3 out of the 4 that correspond to this equation in the 3-set instance. So now let's take a yes instance of the gap max 3-line problem. So the opt, let us say k star, and we know that is k star of the equations are satisfied by some assignment, and k star is greater than equal to 1 minus epsilon times m, the total number of clauses over here. This implies that the corresponding 3-sat instance, or say max 3-sat, I should call this, because we are trying to maximize the number of satisfied clauses. This has opt of phi is equal to, well, we have satisfied k star, and that is 1 minus epsilon instances. So we have the corresponding 4 k star clauses are satisfied. And for the remaining, which is m minus k star, you satisfy 3 out of the 4 clauses, right? At most 3 out of the 4. I should be a little more careful here. If the equation is not satisfied, then you'll have exactly 3 clauses are satisfied, not at most. Okay, not just at most. So that's what this is from the non-satisfied equations. Okay. So now what does this give us? This implies that opt of phi is greater than equal to 4 times, well, k star is at most 1 minus epsilon m. Well, let me rewrite this first. This is equal to 3m plus k star, which is greater than equal to 3m plus 1 minus epsilon m, which is greater than equal to, or rather I'll write it as equal to 4 minus epsilon times m. Okay, so opt of phi is greater than equal to 4 minus epsilon. Now, so that means this goes to greater than equal to 4 minus epsilon out of 4m clauses being satisfied in the SAT. Now let's look at what happens to the no instances. In this case, the opt say is equal to k star, which we know is less than equal to half plus delta times m. Now the same thing holds, lies opt of phi is for the satisfied k star you get 4k star plus 3 times m minus k star for the non-satisfied ones. This does not change. The only thing that changes is the value of k star over here, which is less than equal to 3 plus half plus delta times m, which is equal to 7 over 2 plus delta m. Okay. So that means that via this reduction that we have just stated, what we get are instances of SAT, max 3 SAT, that lie in one of two bands, at most 7 over 2 plus delta, or greater than equal to 4 minus epsilon m. Okay, and it has 4m clauses. Now what does this give us a gap of? The hardness of approximation result, because we have shown a reduction from some NP-hard problem, is the following. is equal to 4 minus epsilon, or rather let me put it as the no over yes instances, which is 7 over 8 being the higher order term and plus some epsilon prime. You can verify that this is indeed the case, where epsilon prime is some constant that depends upon delta and epsilon. And because they can be made as small as possible, epsilon prime can be made as small as possible. So this shows that gap max 3 sat can't be approximated to better than 7 over 8 plus epsilon prime if p not equal to np. And by approximated, I mean using a polynomial time algorithm. It should not be a gap, it's just max 3 set cannot be approximated. Now it's worthwhile to note, and you might have guessed this already, that if just a random assignment like we did in the max sat question, if you specialize it to max 3 sat, or exact 3 sat, will satisfy 7 over 8 of the clauses in expectation. Okay, and it can be de-randomized, so there is a deterministic algorithm that kind of gives you a 7 over 8 approximation, and anything better than 7 over 8 is NP hard. Okay, so this is a really strong threshold result for max 3 sat in terms of hardness versus approximation, and this is why we say that the max 3 sat question is kind of settled. So this kind of brings us to the end of this section, where we went through this proof checking view of the PCP theorem, and we figured out that that was just another way of getting a three-lin or a certain constraint satisfaction problem, and using the gap version of the problem that the PCP theorem gave us in hand, we could show a reduction to max 3 set. Now the important point in this, I guess to emphasize again, is the fact that the particular PCP that we had carried out tests of a very nice form. That is, it just looked at over here, it just looked at the XOR of some 3 bits at a time. And this is what helped us give the hardness result for max 3 set that I just showed. Okay, and often it will be the case in hardness of approximation that you want a PCP with certain properties of this form. For instance, if I want to show hardness of a max cut problem, I will want a PCP that checks 2 bits and says yes or no. Okay. Now, speaking of the max cut or querying just 2 locations and checking yes or no, uh, it turns out that the 3 query bits in this particular theorem is actually crucial. Okay, and you cannot get it to 2 query bits because that problem is a polynomial time constraint satisfaction problem. So we'll see a little more of this when I come to the unique games conjecture about what happens to 2 queries. For now, let's move on to the next section where I want to tell you about the label curve problem. Okay, so now in the third part, I'm going to tell you about the label curve problem that I mentioned before. Now, this is a really important problem from the point of view of hardness of approximation, because using this problem, various other hardness of approximation results have been proven. So let's go over the problem, and I will tell you later how it relates to the PCP theorems that we have seen before. Now the input is a graph. In particular, it's a bipartite graph with 2 vertex sets v1 and v2 for the left and the right, and we have a few other parameters that I will describe in a moment. Okay, now The goal as such is to assign a labeling to the vertices from some alphabet set sigma. So I'll call the labels by a function sigma, which goes from v1 union v2 to sigma. Okay, so sigma of u is the label of u. Now you have a constraint on every edge. Okay, so if I assign a label sigma u to the vertex u, and I assign sigma v to the vertex v over here, the pi e constraints actually tells whether this is a valid assignment of labels for that particular edge. Okay. So pi e, in particular, we can also split the alphabet set as being sigma, say v1 to sigma 1, which are the vertices that which are the labels that the left hand side vertices can receive. And it takes v2 to sigma 2. Okay, and pi e is a constraint that maps a label in sigma 1 to a corresponding label in sigma 2. Okay, so what do I mean by that? It actually tells you that if I assign a label to a vertex u, then what is the corresponding label that v must be assigned, okay, so as to make the constraint valid. So an edge is satisfied if, so let me call the edge uv, where u is in the left hand side and v is in the right hand side, and it is satisfied if pi e of sigma of u is equal to sigma of v. Okay, now every vertex when assigned a label on the right hand side determines uniquely, because pi e is a function, it determines uniquely what the label should be to its neighbor on the right hand side. Okay, and these pi's can be different for every single edge emanating from u. So for instance, if you have something over here v prime, you will have a different constraint over here. So sigma of u might match to some sigma of v, but it will match to some other alphabet that v prime should be attached to via the constraint pi e prime. Now what is the objective over here? Oops. As expected, we want to satisfy the maximum number of edges. Okay, and I can express this in terms of the constraints that I've written out as the objective function. Suppose I take uv as the edge, then I want the number of edges where pi e of sigma of u is equal to sigma of v, and the maximum is over the labelings that are possible. Okay, so I hope this is clear. You might think that the problem as stated is quite general, in the sense that there's no relation between the constraints for say pi e and pi e prime. There's a label set which as of now can be arbitrary, so on and so forth. It turns out that this kind of generality of this problem is what allows us to prove hardness of approximation for many other problems starting from this. Now, given this definition of label cover, we can state the PCP theorems that I've stated before in terms of a label cover instance inside. Okay, so let me define the gap label cover problem. Which is going to be defined naturally as you would expect. So if you say gap 1 epsilon label cover is going to be the problem is that you want to in polytimes given an instance of label cover problem, you want to say of course in polytime yes, if there exists an assignment that satisfies all the constraints, that satisfies all edges, then we know if for all assignments you satisfy at most epsilon fraction of the edges. Okay, so this is the natural gap version of the label cover problem. Now the PCP theorem that I first stated for gap max 3 set can be stated in the following form, and I'll call this as form 3. There exists a constant epsilon naught such that gap between 1 comma 1 minus epsilon naught of label cover is NP hard. Okay, that is, it is difficult to distinguish between label cover instances that are perfectly satisfiable versus you can satisfy only a 1 minus epsilon naught fraction of the instances. Now an important parameter in a lot of label cover constructions, although it's not important directly for us, is the size of the alphabet, okay, which is sigma, and the instances that come up via this label cover in this PCP theorem have the size of sigma, which is sigma is the union of sigma 1 and sigma 2, the number of elements in that is a constant, which depends of course on this epsilon. So the smaller your epsilon is, the smaller your label cover alphabet size will be, because 1 minus epsilon is closer to 1. Okay, so this was the original form of the PCP theorem that was proved. And actually if you go back to your gap max alpha problem, max 3 set problem, sorry, between, we had seen that it is 1 versus 1 minus epsilon naught, can say that it implies some version of the gap label cover. Okay, for appropriately chosen graph instance. Okay, and this is for some epsilon 0 prime that depends upon epsilon 0. Okay. Now notice that we cannot get down to less than 7 over 8 over here for max 3 set, because there is always an assignment that satisfies at least 7 over 8 fraction of the clauses. Okay, what we would like ideally is to reduce the soundness parameter or the lower gap of the label cover problem to be much lower in order to prove hardness of approximation results. So that required one further step, which is often called parallel repetition, and it looks like on the surface level as something similar to the gap amplification that we did for clique. Okay. But it's a lot more involved when it comes to label cover. This was proven by Raz, and the result is the following. states that gap 1 comma epsilon label cover is NP hard for all epsilon greater than 0. Okay. That is, you can get the gap instance between the completely satisfiable instances in the yes instance to the unsatisfiable instances to be as large as you want. The trade-off is that the alphabet set size of the label cover increases. So if I remember right, this increases as something like 1 over epsilon raised to order. But notice that for epsilon being constant, this is still a constant. Again, the details are not really crucial to us. It will be somewhat crucial if we see the reduction to set cover, okay, which I don't think I'll have time for in this lecture. Now, this strengthened PCP theorem is the starting point of, as I said, of many hardness of approximation results. In particular, set cover uses the following. So this is an even more strengthened version of this, which states that something like for all constant t greater than 0, and we are thinking of any such constant, gap 1 comma 1 over log raised to c label cover is NP hard, where the alphabet set size is something like order n. The notable difference or the strengthening is that you have a really large gap. It's not just constant epsilon with the alphabet size still being polynomial in n. So this is just a detail which you can ignore for now. So the reduction for set cover that is given in the textbook is starts from a slightly weaker version of the PCP, basically because the textbook was written when this strengthened version was not yet proven. But the reduction is still the same. You take a label cover instance and come up with a set cover instance. So I'll skip the details because it might be too much for this particular lecture now, and I will move on to the unique games conjecture. Now the unique games conjecture is a conjecture, okay, so and it states that a certain problem is NP hard as a conjecture. Now what is the problem? Well, it turns out it is very similar to the label cover problem, but it is a special version where the constraints on the edges take a very specific form. So basically it's a label cover problem. So this is one form of stating it. Are bijections. Okay, so pi e from sigma 1. So the left alphabet and right alphabet by definition therefore have to be the same. And pi e, because it's a bijection, it's a exact one-to-one onto map, is a permutation. So basically you need to permute the labels in a certain way in one to get the other. So this is the unique games conjecture was introduced because label cover itself was not sufficient to prove hardness of approximation for various problems, including the max cut problem. Okay. Now, a simpler way to remember the unique games conjecture is to look back to the NP hardness result that I told you before of in the Pcp verifier form. Okay, so recall second form, which is kind of easier to remember. So we found that this problem is hard. And the conjecture basically states that you look at a two-lin version of this and a gap version. Now, in the max two-lin version of this, I'm going to allow it to be over a larger alphabet. Okay. So in this, the constraints are of the form some xi minus some variable xj is equal to cij, but you go mod k. Now in the three-lin version, we had only mods. You were going always mod 2 because it was over f2 and the alphabet set was just 0 or 1. Here you need to go to a larger alphabet. Now the unique games conjecture states that in its two forms is that label cover, or let me put it like this, for all epsilon delta greater than 0, there exists k such that, in fact I'll remove the delta, gap of 1 minus epsilon comma epsilon. So let me call this as unique game. The word unique comes from the fact that there are bijections over here. NP hard with mod sigma equal to k. Okay, so k depends on epsilon. So basically, it's the summary is that it says that label cover with bijections is NP hard. And secondly, in terms of the max 3-lin, says that in terms of max 2-lin, sorry, it says that for all epsilon delta greater than 0, there exists k such that there's a gap version of the max 2-lin problem. Again, it will be between a 1 minus epsilon and delta of k is NP hard. And the point to note is that these are conjectures and both are equivalent. And this is a starting point for stronger hardness of approximation results for problems such as max cut. So you do get an inapproximability result for max cut via the label cover problem in its original form, but the inapproximability result gets you to something like 16 over 17. With this UGC, which is a conjecture, you can get it all the way up to the Gomans-Williamson constant exactly. So that is more or less what I wanted to say in this lecture about hardness of approximation. The last parts of it might seem a little heavy, but I just wanted to give you a little window into how you start or go about proving these hardness of approximation results. So to summarize, we have the initial version, which is gap problems, especially gap max CSAT in its PCP theorem gives us that is NP hard. Then you have the proof checking view, which states that PCP, the class of PCPs using log n randomness and a constant number of queries, captures the class NP, which is a probabilistic version of the original definition of NP. And on the third set, you have the label cover problem and showing that gap label cover is NP hard. Okay, so that kind of finishes the lecture. And it also turns out to be the end of the set of official lectures for the course. We might meet a couple of times after this in which we can go over doubts from not just the last unit of the course, but also the rest of the course as required. Besides that, there are a number of topics that we have not covered through the course, and I might post something in the Piazza page that points you to further references as required. Okay. So that's all from me now. And